All right, so that is kind of NumPy. And in your guided project and even in the Colab notebooks today, we're going to be working a lot with NumPy. It's probably one of the most important libraries to know. All right, so basically, why NumPy? It provides us with a lot of linear algebra tools. And everything we do in machine learning comes down to some sort of linear algebra application. So we have Fourier transforms, as I said, finding the inverses of matrices and things like that. All of that we will make use of in our ML models. And there are bigger libraries like TensorFlow and PyTorch that you may have heard of. These are like our larger machine learning libraries. And all of these libraries make use of NumPy to basically perform operations on what they call tensors, which we can just think of as like an array for now. And basically, it just optimizes a bunch of our code for us, and it produces the most efficient matrix multiplication we can have for Python. Okay, now the next big one is Pandas. And Pandas is mainly used for data manipulation and analysis. So NumPy helps us do a lot of the computational work. Pandas actually helps us with like extracting our data from whatever format we have. So most often what we're going to end up using Pandas is for but getting our training data into a certain format so that we can then run it using NumPy and these other machine learning libraries. So some features of Pandas are data reshaping, pivoting, merging, and joining data sets. So probably the most important one we'll use in both of these tracks is the merging and joining of data sets. Sometimes your data is going to be split across multiple files. Pandas will automatically join all of that for you together. Data reshaping basically allows us to drop certain columns or rows from our data. So let's say you find some data with a lot of noise in it, you can just drop that row. And Pandas lets us do that very easily. And then briefly, I talked about data frames, which as you can think are just like this data structure for a two-dimensional table. It's just a table. It's a complicated way of saying we have a nice table that we can access. All right, the next one is matplotlib. This one is the plotting library that we like to use. And surprisingly, you may be a little interested in why this is important for machine learning. And so plotting the results of our ML model can actually be very important. We like to see the difference between, let's say, our training loss and our validation loss. So the differences between errors is something we like to see, because if we see a really large gap in our error, this can indicate that something is wrong with our machine learning model. And it also allows us to visualize how our model is improving or becoming worse as we train it for longer and if we give it different data. And so that is the entire purpose that we have matplotlib, is to help us visualize patterns in our data. Another use that you may see matplotlib kind of used in is we will look at our data even before we train it on an ML model to decide what type of machine learning model we want to use. In the case that we print our data and we see like, oh, this follows like a nice linear trend, we may want to use linear regression. If we see that, oh, there's like a lot of clustering going on here, we can see like these 4 or 5 distinct groups, we may then decide to use a KNN to classify these and categorize these. So that's what matplotlib is used for. And then if you ever do physics 4AL, you will use a lot of matplotlib. And basically all you have to do is create bar charts and scatter plots for velocity versus time. And that is another feature. Any chart you can dream of, matplotlib probably has it. So error bars, bar charts, histograms, and all of that jazz. All right, now this is our first machine learning library, and this is scikit-learn. And this generally implements more basic machine learning models. So things like regression, classification, and model selection. So scikit-learn will have like a function that will automatically train and produce a KNN for you. It has a linear regression feature. It has a logistic regression. They also have decision trees, and they also have functions that will optimize your model for you. So if you remember, I think in the KNN workshop, we talked about something called a hyperparameter. And what scikit-learn provides is it provides a function that will find the most optimal hyperparameter for you, for your model. So that is what scikit-learn has. So as we said, this is all about classical machine learning. Basic things: linear regression, KNNs, logistic, and decision trees. It does support both supervised and unsupervised machine learning algorithms. And this is more often used for data mining and data analysis because these models are more classical. They may not be as rigorous or robust for more advanced data sets. Now, probably the most popular one, or the second most popular one, is TensorFlow. And this one was developed by Google Brain. And the entire idea is it is high performance numerical computation. And all this should mean is neural networks. This is what we like to use for neural networks because things are so fast. And it is basically built to build neural networks. If you want to do like classical machine learning, look at scikit-learn. If you're looking to do more like work in neural networks and simulations and stuff like that, TensorFlow is what you want to do. And as we said, TensorFlow likes to use its custom thing called a tensor. Just think of it as an array for now. A tensor is basically like a vector in array, and it runs all of its computation on these. So as we said, it can train and run deep neural networks. And basically, half of modern AI is neural networks now. So it's very widely used, and it is also used a lot in research. So if you join a lab, you'll probably end up using either TensorFlow or PyTorch during your research to train all these machine learning models. Do you want to take it?
Sure. All right, the alternative to TensorFlow is PyTorch. It's an open source machine learning library based on Torch, which is a library that is implemented in C with a wrapper in Lua. This was developed at Facebook and made open source in the last decade or so, and is now widely popular both in industry and in research. So again, like Venkat said, you are going to see this if you ever work in research. You're going to see one of these two libraries at least a couple times. So we use PyTorch because it has a ton of tools, libraries, and other things that support computer vision, NLP, and many more different ML programs. And it allows developers to perform computations on tensors with GPU acceleration, and also helps in creating computational graphs. And now we get to the demo.
We're going to swap to your computer because both of us have to leave.
Not right now, but before.
Where's Eric?
I have no idea where Eric is.
Whoa, boy.
Anyway, could you give us a moment? In the meantime, as always, we have the beginner cluster linked up here. This week, we have both the skeleton code and the answers linked. So if you want to be looking at the answers for it and you're not really coding along, just like seeing what we're doing, you can do that. Alternatively, I would invite you all to follow along and start with a semi-filled in notebook. And then as you're working through, you'll begin to actually be responsible for, making the changes that it talks about. So give you guys a little bit longer.
We forgot to ask, do any of y'all have any questions, comments, anything like that about libraries? Hopefully it's all been reading off of the slides so far. Yeah.
So like, how do you decide which library to use?
Yeah, so basically each of the libraries you cover has very distinct functionality. So if you want to do data manipulation, that's like Pandas. If you want to do classical machine learning, that's scikit-learn. If you want to do deep learning or any sort of neural networks, it is up to you to decide between TensorFlow and PyTorch. Personally speaking, for experienced TensorFlow is usually a little easier to learn than PyTorch. So like if you're first getting into things, TensorFlow is probably better to choose. And then NumPy is basically used for if you have a Python script, probably import NumPy.
Yeah. So yeah.
The skeleton.
The man himself.
Man, myth, legend. Only like 2 minutes. No, you're good.
Yeah, something else I will say is that regardless of if you're choosing like TensorFlow or Python, probably the best way to learn it is by just diving in and like getting your hands dirty, and like going in and making your own model using one of those frameworks. So
TensorFlow has some really good online tutorials. Like where Google itself has written tutorials and like custom data sets or like very popular data sets, and they teach you how to implement like neural networks. in
And we'll switch over.
So starting off with that, you'll learn
We're gonna use his or not? Up to you. But
Yeah, whichever one works better for you guys.
Like, why do the slides say Jordan hates TensorFlow with the learning path?
because he does.
I mean,
Why?
yeah.
If it's easier to learn.
I think the major gripes against TensorFlow, I personally have used TensorFlow much more than PyTorch, but from my understanding, the major gripes is the model is compiled every single time, if I remember correctly. And, you know, it's a little less customizable than PyTorch. So in research applications, at least at UCLA, PyTorch is being used much more. And because of those reasons, it's kind of filtering out into industry. So from my understanding, it seems like PyTorch is going to be the more dominant library lately, but it's all in fun. It's all in fun.
If you're developing custom models, you it's more customizable. Generally, research here also does focus on PyTorch a little bit more because if your research is developing like a new machine learning model, you want that customizability. There are, personally, when I was doing research, I used TensorFlow because my research is not focused on developing a new model. It was just like deploying an existing model and like testing various things about it. So it's very dependent.
A lot of times in computer science, you know, not just with regards to machine learning, but things that like, you know, are maybe a little more beginner friendly and easy to use, usually accomplish that by sort of sacrificing like some of like the nuance and like the finer grain control, you know, because if you're like just starting out in machine learning, you don't want to have to be, you know, like, I don't know, tuning a bunch of hyperparameters and a bunch of stuff like that. You know, you want just like a relatively simple, like write a couple lines of code and get it like started, you know, and that's not true just for machine learning. That's true for pretty much anything that you're going to try and do. But what you'll usually tend to find is that, you know, as you get like more experience with it, you'll begin running into more and more edge cases, and you'll begin to realize that, oh, you know, maybe I would like a little bit finer control than this gives me. And then you'll move on to like a slightly more complicated, you know, library or framework. So
a way to think about it is programming languages, like not the case at UCLA because UCLA likes C++, but at other universities,
do you want to share?
people will start with taking a Python or a Java course,
if you want,
and then they'll migrate into C++ as they go more advanced and more in depth.
I like prep the whole thing, but like low key, like how much? Like,
Wow.
Out of curiosity, does anybody here actually like programming in Java?
which is like the bulk of it.
So we got two.
It's gotta be early because
It's higher than normal.
It's okay. I
you
just
just cover
take
like
Java,
half
but
of the
that's
time,
just a personal
or
preference.
just cover up to like when you're comfortable with. If not, I can just do
Well,
one.
also Breaker also just got, so if you want to teach any of like the skeleton, I know where. Okay. All right. I can, so. Okay, so just put up the skeleton code.
This video? Okay.
Like 7-ish, some type of.
That's the SU.
No.
So I'm gonna do the whole thing. I mean, I'm happy to simulate, but if you want to do this, it's pretty dumb. I'm really crazy about it. I'm really crazy about it. Okay, don't I just get started? Step with it. So it's when I do this video, right? This means we put everything in that level wherever I have. Okay, let's make it happen.
Oh, that's.
I think it's on the bottom.
Don't worry about it.
I don't know why he's doing this. I don't know why.
Sorry, y'all. We're taking
Maybe try.
one moment.
Maybe try his because I don't know how to
If
do it.
No, that's not. That is.
What?
That will work very well upon initial creation of your hash table. But once your hash table becomes full and you have a lot of collisions,
Bro, what's the show about? Every time you're putting something in, you're adding.
Alrighty.
yes.
Sorry about that, y'all. So we're going to get started with a little introduction. Mostly what we're going to be covering today is NumPy and NumPy arrays. So as you guys just heard, NumPy is used for a lot of linear algebra and stuff like that, right? Because I'm not sure how familiar you guys are with like matrices and other things like that, but the operations required to, do pretty much anything with them tend to be pretty repetitive, and, arrays in the way that we use them tend not to be set up like super great for doing efficient, matrix multiplication. And if you're dealing with a lot of data or doing something a lot of times, you probably want something a little more efficient than writing your own code in Python, which is where NumPy is going to come in for us. So run anyway, you guys can trust us. So as you can see here, we've linked the API reference, which is basically just a reference page that is going to tell you how each function is going to behave and like how the different objects you can make are going to behave and stuff like that. So jumping on in, the backbone of NumPy are NumPy arrays, right? This is an array type that can have n types or n different dimensions, right? Which is going to be a collection of items that all have like the same type. So that means, they'll be like all integers, right? Or they'll be all floats, and so in NumPy, when we're talking about like the dimensions, we're going to refer to them as axes. If you want more, again, check out the reference documentation. So there's several ways that we can make a NumPy array, right? So the first way we're going to do it is we are just going to pass in an actual Python list, right? Now, what this is going to do for us is it's going to say, hey, I noticed that you have a Python list right here, right? That's great and all, but I think that you're trying to convert me to a NumPy array, which is probably going to be a lot more useful. So I'll go ahead and do that for you, right? So we pass it in, and one thing to note is that because it's multi-dimensional, what we're doing here is we are passing in the 1, 2, 3 list inside of another list, because we're basically just telling it like, hey, we are doing, we are taking our array, and inside of it, we are going to have one dimension that is of length 3, right? And that is similar to how we are going to be creating a 2-dimensional NumPy array, right? Now, as you can see up here, it made a 2x3 NumPy array because both of these guys have dimension 3, right? They both have 3. Yes. You can't access the notebook. That is very odd. Let me. Oh, are you looking at the answers or the skeleton code? Skeleton code. Skeleton code. The skeleton code should be open to anyone. I realized the answers were not. So maybe you were looking at the answers that had restricted access, but now you should be able to access both the answers and the filled in notebook. Interesting. I'm not quite sure what's up with that. That should if anything make it worse. You can talk with us after the fact about the specifics of what's going on, but for right now, can you access it? All right, beautiful. So now we're going to go ahead and, this is where we get to the exercise portion. Based off of these examples, we want to make another 1x3 NumPy array containing any values of our choice. How might we go how might we go about doing this? Does anyone have any ideas or suggestions? A 1x3 array. So have we already made a 1x3 array? Yes. How do we do that? I mean, you guys see it up there, right? Does someone want to walk me through what the parts of this code are doing? No brave souls? No one? All right. Well, I'll pretend I'm, oh, yes.
Sure. Yeah, first just like give it a name. I just did ARR3.
Array 3, beautiful,
Yeah, equals.
equals,
Yeah, then n dot array.
array,
And then parentheses. And then with like the big parentheses.
the brackets,
Yeah. the
brackets.
Brackets, yeah, brackets. And then I just did like 1, 2, 3, like 1 comma 2.
So you did this?
Yeah.
Alrighty. So it seems to run fine, but call array 3 dot size. It's going to tell us just 3, not 1x3. Now, why does anyone remember why this would be telling us that this is just an array of size 3 instead of 1x3? What is the difference here? Yes, exactly, right? When we invoke it up here, we have another pair of brackets around it, right? And so when you pass in a Python list to NumPy and you say, hey, turn this into an array for me, the first thing that it does, right, is it's going to iterate over every single value in the list and try and figure out how it's supposed to put it into this array, right? So if we get rid of the outer brackets, when it's going through the array, it's gonna be like, hey, you know, this is just 3 values, right? So this isn't really anything that we need like a matrix for. We can just, you know, put this in here and it's just going to be something of length 3, right? It's not, it doesn't really have dimensions because there's just 3 values to it. But if we're doing it like this here, where we have, you know, an outer list, and inside of that list, we have only 1 value, and that value is a list with 3 values inside of it, all of a sudden it's going to look at it and be like, okay, so this list has 1 thing in it, but that 1 thing is also a list, so that means we need another dimension for it, right? And that is how we're going to get a 1x3.
You need to call the shape.
Yes, not size. That is actually so my fault. 1x3. So as you can see, I was calling size, not shape, which is why I gave us just a 3. What it should look like when you call shape on it is just 3 comma, because that's how it denotes, you know, 3 within only 1 dimension. Any questions about this? No? All right, beautiful. Oh, one last thing I wanted to point out is you may notice here that we put an NP in front of array. You might be thinking to yourself, can't I normally just call the array function? And the answer is, well, it's kind of complicated. But essentially what we're doing here is up here, we import NumPy as NP, right? So that's basically telling our notebook that, hey, there's this, you know, collection of files, NumPy over here. And whenever you see an NP, it's referring to something in those files. So if we want to do something from it, like NumPy has like the array method, you have to do np.array, because if you just do array, it'll be like, array, I don't know any array, I don't know where to find it. But if you do np.array, it'll be like, oh, you know, this is saying that inside of NumPy, there is an array function. So we can do some very basic operations to our arrays. So the first operation that we can perform is addition. Now, with addition, if you have 2 arrays that are the same size, and you try and add them together, it will go element by element and add the elements together, right? So as you can see here, we ended up with 21, 32, 43, and 54 because we added 1, 2, 3, and 4 to 20, 30, 40, and 50. Now, with that in mind, $1 million question, Who thinks they know what the subtraction is going to output? Really? I would hope that at least one of you has the bright spark. And yes. You nailed it. How did you know? What are we doing here with the subtraction? Wonderful, wonderful, wonderful. See, there's a courageous soul who's willing to stick their neck out in front of the entire crowd. I love it. Now, also, we can do scalar multiplication. Now, scalars, if you remember, are just any numerical quantity. I mean, like in physics, a scalar is a quantity with like no like direction. Think about like speed versus velocity, which is a vector, right? But for our purposes, we can just think scalar just means like a normal number. Now with scalar multiplication, I would like to see another brave soul tell me, what do they think scalar multiplication is going to do? If I do 5 times A, what is that going to do? Any guesses? Yes. Wow, you guys are killing this. See, I don't know why we're not getting more participation. You guys have nailed every single question. We are going to be multiplying each element of the array by 5, right? So instead of 20, 30, 40, 50, we get 100, 150, 200, and 250, right? Now, finally, this one's a little bit more difficult. We have Boolean comparison. Now, does anyone want to hazard a guess as to what this might do based off the behavior of the others? Yes.
True, false, and false.
Yes. Beautiful. And how did you get true, false, and false?
So like you compare each element to like whether it's smaller.
Wonderful. You are absolutely nailing it again. So when you are doing a Boolean comparison like this, it is going to, again, go on and apply that operation on each individual element in the array, right? And as you are hopefully aware, 20 and 30, they are actually less than 35, but 40 and 50, this one got me, are more than 35. So unlike many other matrix languages, the product operator is going to actually be operating element-wise on NumPy arrays instead of doing a matrix product, which can be performed using the @ operator or the dot function or method. Now, first of all, who knows how matrix multiplication works, or who remembers? Because I imagine at least some of you have been taught in the past. You may or may not remember. It really isn't that important. But what is important is knowing that matrix multiplication works very different from, like normal multiplication. It does not work the way that you would expect. And that is really linear algebra. But with NumPy, they decided to make it, a little bit easier on us. And the product method is going to operate sort of like exactly like you would imagine, right? If we have our array A, that's 1, 1, 0, 1, and B, which is 2, 0, 3, 4, it's going to go element-wise, which means it's going to multiply each one of the elements together, assuming that they are the same size. And again, for all these methods, if you're using 2 different matrices, there are probably going to be some constraints on the dimensions, right? Because if you're doing, element-wise multiplication, but, like the elements are not lining up, then you might have a little bit of a problem. Now, with that being said, does anyone know what A times B is going to output based off that spiel I just gave? Any brave soul want to hazard a guess? Alrighty, so we have a bunch of cowards, and we are going to go ahead and run, I guess. And oh, yes,
We're not cowards.
beautiful. Oh, so do we have math?
Yeah, so if I will just want to so like 2, 0, 0, 4. So like 2, 0 is like the first.
2, 0 for the first row. Gotcha.
And then the next row is like 0, 4.
Beautiful. Nailed it. If we run it, see 2, 0, 0, 4. Are you sure that you're not looking at the solution? But no. So that is how it works. And now for matrix multiplication, it is going to go through and it's going to be, instead of doing it element-wise, you are going to go based off of the rows and the columns. So if you have a matrix that has X rows and Y columns, you must multiply it then by a matrix with Y rows and then some number of columns. So basically, the first matrix is being multiplied by the second matrix, and the first matrix has the same number of columns as the second matrix has rows, right? Now, this conceptually in linear algebra corresponds to like mapping from one dimension to another dimension. If you are interested, I would recommend watching 3 Blue 1 Brown. He describes it much more eloquently than I could right now. But what we are going to do is each column in the first matrix is going to be multiplied by each row in the second matrix, which is why they have to have the same number of elements. So with that rather lengthy mouthful, does anyone want to hazard a guess as to what this is going to multiply out to? Any guesses? No? All right. Let's go ahead and run it. Let's see, it outputs 5434. Ooh, mysterious. Well, that wonder how we got there. And Eric's gonna take over and explain that for you guys.
5434. Yeah, so matrix multiplication. Yeah. I'm not hearing the hype. It's all good. 33 is it's not. Oh yeah. You took the base go. Okay. Anyways. Yeah, so in terms of matrix multiplication, again, we're not really like a math class. Essentially how it works is you can sort of think of like matrices like boxes, and you need to sort of line it up a little bit. It's really hard to do this like by talking, but essentially all you really need to know as of now is like matrix multiplication is really different. If you want to look it up, you can. If
There's no space.
there's no room.
Space.
Ironically, I'm pretty sure there's like a linear algebra class that comes up before this, so we're gonna like try to like steal their notes, but our presentation's blocking that, so
It's 31A.
that's 31A.
They're not gonna be mad if I erase this.
These guys stink. All right, but anyways, so
This doesn't reflect the views of.
oh yeah, I do not speak on behalf of ACM AI, but there's some very lovely people in Math 31A.
These are the opinions of Eric and Eric alone.
Yeah, I want.
Like them, take it up with them, not me.
Yeah, I went to CC. Loki enjoyed it. Anyways, so matrix multiplication, just know that it's very different. You again, this is beginner's track, not a math class. That's all you really need to care about. And in regards to matrix multiplication, there's actually different notations for how you do it. You can probably see that this like A add B. Can I zoom in on this? Let me see. Yeah, there we go. As you can see, like we have like an A add B here. It's really eloquent. It's really pretty, right? That's because the developers made it that way before. If you wanted to do matrix multiplication, you'd have to either call the dot method or you'd have to call the matmul method. So if you're working with an older version of Python, which is kind of a bit weird, you would do these methods right here. But anyways, more methods. Essentially, in regards to arrays, there's some. Yep.
Yeah, I have a question. How
Sure.
do you solve the inverse matrix using NumPy?
Inverse matrix.
There are some library functions in NumPy. I think if I remember correctly, it's np.linalg.inverse. That'll give you the actual inverse, and there's another that you'll use in some courses in the upper divs that'll do pseudo inverse, which I think is basically the same, just like p inverse rather than inverse. So.
Wonderful. Anyways, so back to
This is a way to this is a way to cheat on your homework.
yeah. That's why they don't allow coding in 33A. I asked, don't worry. Take it with Chongshi Wang though, if you can. Anyways, so in regards to our ND array class, we have a couple shortcut functions that make a bunch of operations very like easy and straightforward. So for instance, we have let me just run this to make sure that this demo works. So for instance, if I wanted to add up all of the elements to my array and see like what the total would be, I can just call the sum method and it would do exactly that. As you can see, we have our 2D array. It all adds up to 9. If I wanted to find the minimum value of my array, regardless of how many dimensions or whatever I want, I can just call min. And on the contrary, I can do the exact opposite if I wanted to find the maximum by calling the max method. So if I do that, as you can see, of our little 2D array here, our biggest value is 4. It does it just like that. So you don't need to like write any method to do it. It's already pre-installed. And that's the beauty of libraries. But anyways, now this is where things are gonna not necessarily get a little more complicated, but there's a little bit of notation that comes with working with this library. Essentially, when you're working with a multi-dimensional array, you're probably going to be thinking like, okay, like you can sort of think about like a multi-dimensional array in sort of an idea of like rows and columns. You may have like heard of in like CS31 and 32. But in regards to like data sheets like these, we'd like to think of them more of like axes. And they're pretty much exactly the same as your math class, where like we have rows as your axis 0 and columns as your axes 1. It'll make a lot more sense when you look at the code right here, but this is just the general notation, if that's cool with y'all. Oh yeah, but if y'all I know like library methods can get like pretty dense, so if y'all get like bored at all, please raise your hand and like I can do a little dance or something, just to brighten up the mood. Anyways, so we have this 2D array here called array2, and let's just establish that right here. First row right here will be 1, 2, 3. Second row will be 4, 5, 6. And then as you can see, this is a 2x3 array, meaning 2 rows, 3 columns, right? So if I wanted, for instance, to get the sum of all of the values in my first row, then I would access axes at equals 0 right here. Or wait, did I do that right? Yeah, okay. So what this array2.sum with axes equals 0 means, in regards to this nice little diagram that we have up here, remember that our axis 0 is going to refer to our rows and our axis 1 will refer to our columns. So if I argue that I want to add up my axis 0, this means that I just want to add up all of my columns, for instance. So I'm going into every row, getting every element, adding them up for all the rows. And on the contrary, I can do the exact same thing with axes equals 1. It would do the exact opposite. So for instance, if I delete this and add a 1 here, now I'm going to be summing all of my rows right here. Just like that. And again, this is just like library functions. You can just plug and chug, replace things as you please. So if I wanted to get the minimum of each row, instead of having a sum method, I can just plug in a minimum method and boom, there you go, right? Pretty much, I know like I'm just throwing a bunch of words. The best way to sort of like get an intuition for this is to generally like play around with it. I'm just introducing these methods. That's fair enough. But yeah, let's move on to some universal functions. As you know, in math, there's a bunch of really fun fun methods. You know, you can put something to the power of e, take a square root or whatever. There's pre-built methods for that. So for instance, if you want to put something to the power of e, we have an exponential function that you can call. If you want to take a square root, if you want to square root every single element inside of an array, you can just call the square root method and it'll do exactly that. If you want to take the sign, the trigonometric sign of every element inside of an array, you can call this sign. And similarly, you can do the same thing with cosine and tangent. There's like a kabillion trig things, and we're not really about that. Yeah. But anyways, general universal functions, are we all chill with that? Or cool. Anyways, let's move on to some actual like things that relate to how we can manipulate our 2D arrays. So as you can see, we've funnily labeled this enough as indexing, slicing, iterating. Anyways, so let's say I have a huge little array, right? And I want to act like there's like 10 elements or whatever in it, right? But I only want the third element. How do I go about doing that? Similarly to Python, if you're familiar with Python, all that you'll do is we'll use this rectangular bracket notation, where the first element will be at quote unquote index 0. So the first element 0, therefore, like the first index 1 is the second element, and index 2 is our third element. So if we have array 3 at index 2 here, this would be accessing our third element. And so given that, man, that is a loaded question. That's crazy. Okay, one more piece of notation here. Let's say I want to access the last element of my array, but I don't really know like how big my array is. How do I go about doing that? The way you go about doing that is, for instance, if I do a negative index, this will start at the end of my array and work inwards. So -1, given this array right here, this should return the value of 9 because that is the back of my index. So boom, 9. And if I want the second to last, then I would do -2. So boom, we have 8 now. And man, that is crazy. I don't know why they dropped like, it's a loaded question. Given that if I ask this question, given all of the information I've given you, you will not be able to solve it. Do we have any ideas for how to solve this exercise? If not, it's completely chill. Or if you want me to do like a cartwheel, I can try. I've never been able to do a cartwheel, but yeah. Tonight's the night. I don't think Christian
really.
from PT would approve, but yeah. No, I'm being all right, all good. So let's say that I want to access the last 4 elements of my array. There's this other bit of notation here. For instance, if I want to get a range of values in an array, let's say I want to get like the first, like all the values between like our first and third arrays. So I want the first 3 values of my array. So I know that the values that I want to start at my first element, so that'll be 0, and I want to end at my third element. So I want all those elements in between. The notation for that is this. So we have a colon representing like, I guess like a dash, you know, like 0 through 3. And you're probably thinking like, oh, why did I plug in 3 if I'm looking for 3 values? Python notation, it's stupid, it's dumb. Essentially, you start at the index and you go up to every index, not including the last value. So if I plug in 0:3, I'll start at 0, I'll go to 1 and 2, but I won't go to index 3. So the way I like to think about it is if I want like the first 3 elements, if the difference of my end and my start is 3, then that'll give me 3 elements, if that makes sense at all. But given that, if I want to get a range of the last 4 elements, all I'll have to do is I'll take my silly little array here and I'll end at the last element here, or I'll end at the second to last element, and I'll start 4 elements before that, not including the last one. So if I do that, I believe this should work. This did not work. Wait, what? That's crazy. I believe this should be a -1. -1, and then there should be a 5, I think. Man, that's kind of crazy. Oh well. Pretty sure. Wait, hold up. Let me do some testing here. Wait, it should just be. Oh wait, I got it. I got it. It's so silly. There we go. All right. So we should have maybe written this better. The notation, for instance, if I want to start at an index of an array and then get all the elements afterwards, you don't necessarily have to fill in every single parameter. All this notation is saying right here is I'm going to start at the 4th to last element, and I want everything afterwards because I don't put any argument to the right of the colon. Is that fair enough for y'all, or cool? If y'all are bored, I can just rant about my pizza and Epicuria. But anyways, so no, I hate the app, man. It's so dumb. Okay, but anyways, again, I don't speak on ACM AI's behalf. I'm just here. But okay, so let's say I have an array. I want to iterate through every single element. Similarly to any other programming language, we can use a for loop. And thankfully, the notation for it is very simple in this language, which is Python. You just do a for loop. So this is just saying like for I is sort of like a variable that stores like what element in the array we're currently on. So all this is saying is for each element in array 3, print it out. And that is exactly what it does. You may think like, okay, but that's cool for a 1D array. How does it work for 2D arrays? Or wait, we're not there yet. So, for instance, when you're working with data, you're generally working with multi-dimensional data. Not every single piece of data can be stored in a single array. That would just be like a really long array, right? So we organize our data using multiple arrays inside of arrays. And so the notation for that is a so. So for instance, like this right here is a single array, and then this right here is another array, and all of those arrays are in one array. So we have one array that stores 2 arrays, and each of those 2 arrays stores 3 arrays, and each one of those 3 arrays stores 4 elements. It's a headache, I know. That's the beauty of Python. Anyways, so given this array 4 here, let's say that I want to access like a certain element inside of this 2D array. You'll utilize a very similar notation. So for instance here, let's say that I want to access, in this case, the second, third element. We'll utilize this notation right here, and boom, we have an 18. So let's break it down here. The first array element right here refers to our first huge array. And then the second one here will refer to the first array inside of the second array, in that huge first array. And then the 2 here will refer to our third element. And this is all due to the fact that we're indexing starting from 0. Is that cool with everyone? Or wonderful. Okay. All right. So anyways, I don't know why they put this here right now, but let's say that you want to slice a 2D array. It's the exact same notation. It's just that if you want to, how do I word this? It's the exact same notation pretty much. So for instance, right here, all this is saying right here is I want to go to my first huge array, and then I want to go to the third array of that first huge array, and I want to get the second to all the elements starting from the second element to the fourth element, because the difference between 3 and 1 is 2, which means that this should output 2 values. Because remember that this does not include the value at index 3 in this case. Anyways, given that, we got a whole bunch of other colon notation here. Yeah, all this is saying right here is if you just want to get an entire array, you can just put in a colon with no arguments and it'll just pass the whole array. And that's just a couple examples of that. And for instance, with a 2D array, you could also pass just a single array argument. So I have 3 dimensions. If I only try to access 1 dimension of those 3, it'll just print out the entire 2D array starting from that dimension. So remember that our huge 2D array looked like this. So if I try to call array 4 at index 1, all it'll do is it'll say, okay, array at index 1 will be this huge array, and then I have no other arguments. I'll just output that. And so that is exactly what it does. So yeah. Let's see here. And then pretty much for iteration, exact same notation here. It's just that if you want to iterate through element by element, if you have multiple dimensions, you need multiple for loops. So let's see here. But the one good thing about NumPy is essentially if you want to iterate through all the elements of a multi-dimensional array, you're probably familiar with the notation in C or Python or whatever, where you have to do multiple for loops. There's a beautiful notation in NumPy where you can just flatten your entire 2D array, 3D, whatever, kabillion D array into just a singular array using this array6.flat method. And then you can just iterate through that. So this is pretty much just iterating through your entire array with the assumption that your entire array is just squished into a one-dimensional array. So you can just iterate through that. And that's one of the cool things about using NumPy. You can just do those shortcuts like that. Let's see here. Okay. All right. Are we still hanging in there, y'all? Or yeah, cool. All right. Or do you want to cover something?
No, I'm just saying, like, if we need to, we can.
Okay, sure.
Not a lot of this is like immediately necessary.
All good. Anyways, back to our wonderful library exploration here. So you're probably thinking like, okay, this is like pretty standard stuff. I can add elements, I can subtract elements, I can print out every element in an array. This is like sort of just like things that you can do. Like, why do I need NumPy to do this? This is where NumPy, a little bit of its like glory comes out to shine a little bit. There are specific NumPy like methods that allow us to do really cool things in terms of machine learning and essentially building models. So let's go through those. These are going to seem like pretty redundant, but these are like, let me tell you, these will like cut down like so much work when you're trying to like build models and stuff. Anyways, let's break it down. So first things first, let's establish this array at index 4. Just as a reminder, it's this huge 2D array or 3D array in this. No, that's 2D array. Yeah, that's a 2D array. Or yeah. Anyways, so if I want to count the number of dimensions an array is, like I just showed right there, it's really hard to do that visually. There's a wonderful method that does that. It's called n dimensions. And let's say that I want to, let's say, what is this here? What's wrong? Oh, the shape. I'm trolling.
No way.
Oh, wait. All right. I'm trolling. Anyways, so similarly to the examples that we showed earlier, the shape should print out the dimensions of our array. Regardless of how many dimensions there are, it'll just print it out. So all this is saying is we have, like I said earlier, 2 huge arrays. Each of those 2 arrays stores 3 smaller arrays. Each of those smaller arrays stores 4 values. That is all this does. And similarly to size, all the size will do is it'll just count the total number of elements inside of the array. If I want to check the data type of the things that I store in my array, then I just do dtype. Pretty simple. If I want to change the shape of an array, let's say that we're working with this array 1 right here. Okay. Let's say that I'm working with this array 1 right here. These are a couple more examples of cool things that you can do with NumPy. Let's say that I just like really hate having multiple dimensions. I just hate it. I just don't want it. And I just want to switch it all into one simple array. I can do that using the ravel method right here. And like, boom, this huge, like, what is that? That's like a 2D array. This is a 2D. The other one was 3D. Oh my God. I did not pass 32. Anyways, so if I have a multi-dimensional array and I want to just switch it into a single dimensional array, I can just call the ravel method and it'll do exactly that. It'll just switch whatever dimension array into a 1D array. If I want to reshape my array from like a 2x3 to 6x2 or whatever, I can call the reshape method and I can pass in how many rows, how many columns, how many, whatever the third one would be that I want, and it would reshape it. And it is not working in this demo. But normally this reshape method is like really beautiful. It just like makes your models and all your data just like work and it's beautiful. But it's not working this time, but that's okay. if you want to do a linear algebra transpose, again, we're not a math class, but a transpose is essentially like flipping your array like backwards if you just like hold two corners and just like flip it. It's weird. If you just Google it, it'll become a lot more clear. If you want to get a transpose of an array, then you can just call the T method and it'll give you the transpose. It's hard to visualize in this example, but you don't really need to care about it as of now. But for instance, if I want to do a reshape or a transpose, but I don't know the size of my array, again, we can utilize that notation where -1 refers to the last element of our array, and we can just pass -1, and it'll just do the job for us. So if I want to reshape using the last element of my array, like, wow, look at that. Reshape worked beautifully this time. Oh my goodness, I could cry right now. Could y'all cry right now? I could definitely cry right now. Anyways, let's talk about other ways to create an array, and I'll hand it off to Gregor because I've been speaking for a while.
We're almost there. We're almost out of NumPy. We're almost to Pandas. We're almost to Matplotlib. Just a couple more segments. Really quickly, we're going to go through some other ways to create an array. We've kind of just used a Python list implementation and then calling the np.array constructor on it. NumPy has a couple of built-in functions that can create an array. So for example, np.zeros will give you an array that is entirely zeros in the space specified. So typically these functions, you'll pass in a tuple, which will represent the shape of the vector that you want in the end. So if we do np.zeros 10.2, we're looking at a 10-row, 2-column vector of zeros, which is generated here. And similarly, we have np.ones, which will create an array entirely of ones. And in this case, we're looking at an array of 100 ones. Finally, there's the function np.empty, which will create an array that is randomized based on the state of memory, really. So this could kind of be anything that is in memory or anything that is kind of randomly generated. So empty is going to be non-deterministic. You're not really going to know for sure whether or not it's going to be a set of values. So if you're going to use np.empty, you may have to clear it out and make sure that you go through and put in the data that you need. With that, that covers kind of the three other major ways of creating arrays in NumPy. And now we're going to talk a little bit about creating sequential data. Creating sequential data is really useful when it comes to iteration and just kind of navigating a data set. There's two methods that we're going to cover: arange and linspace. So arange is a function where we pass in a start and a stop, where the start is the inclusive and stop is not. And np.arange will return an array of all of the values between 0 or between start and stop non-inclusive. So for np arange 0 through 10, we're going to get 0 through 9. We can also specify how big of a step we want to take. So if we want to do every fifth number between 10 and 30, we simply add in the number 5 as a third argument. And that'll get us 10, 15, 20, and 25. It also does accept floating point arguments. However, that's not recommended. If you want to use floating point arguments, or if you have floating point data, we recommend you use linspace, which will basically allow you to specify how many different data points you want in each sample, rather than the total step number between. So if we use a floating point argument, we are not really sure how many different values are going to be in here. So as you can see, it's not 4/5 or -4/5. It's going to be, 5 values there. Whereas if we use np.linspace, we specify start, stop, and a number of values that we'd like returned, and it will always give us that many values between them. So in this case, between 0 and 2, if we wanted 9 values, we're going to get 0, a quarter, a half, and so on and so forth. With linspace, the endpoint, so stop, is now inclusive. So now if you want the same behavior as arange, you're going to want to specify that the endpoint is equal to false. And in this case, that means it'll be a different set of fractions. So now we're going to create a sequence of 30 evenly spaced values from 0 up to including 2 pi. Which function do you guys think we should be using here? Alrighty. I'm not going to call you cowards because I'm not Jackson. Thank you. There you go. So we are going to be using linspace here. Basically, np.linspace 0, 2 times, I think it's pi, and we want 30 numbers, so 30. That will give us this array. So that's a couple of different ways that you can create sequential data. Really just depends on your use case and what you need in that situation, but either of these two functions are sufficient. Now we're really going to just quickly cover conditionally selecting elements. Given an array, you can essentially say, I'd like all of the elements above this point. So given this array 7, we'd like to select all of the values that are greater than or equal to 50. So in that case, we'll have 70, 60, and 50 in array 7 res. And that'll return true, false, true, true, false, false. Sorry, I got confused on that one. Now that we have that, we can basically create that array that we're looking for. And then in this case, if we wanted to do that for, say, any value in array 7 that's divisible by 20, excuse me, entirely necessary. We're just going to take the modulo with respect to 20, and that'll give us the element-wise modulo with respect to 20 of all of the different values. So that is the remainder with respect to 20. So now that we've done kind of all that, let's try and write a really basic softmax function. So as you remember from our logistics regression section, the softmax function essentially applies, creates a probability distribution within a vector that we're given with different values. So it's going to take, for each element z, it will take e to the z and divide it by the sum of e to the zi. So in our case, we can really just, using some of the functions that we've learned, return np.exp array divided by np sum of the exponent of the array with respects to axis 0. And in that case, we've now written the function, and that'll give us our probability distribution. That's NumPy. A lot of stuff that you just learned. You're not going to use all of it, and you're probably going to have to look at the docs again. However, it is a really useful library. I use it all the time now, especially in some upper division CS courses. So I highly recommend getting good at it, or just using it in 33 to get through your homework faster. Like, let's be real. No one wants to do linear algebra by hand. Now we're going to talk more about Pandas. Pandas is one of the primary data handling libraries. It essentially works in its own data type called a data frame, which you can imagine is kind of a spreadsheet, really. We're going to really quickly import Pandas and then just talk a little bit about a data frame. The data frame is a 2D data structure where we can store different types of data. So in each different column, we could store a feature, or some categorical value or a numerical value, and so on and so forth, where each row can kind of be a different example or a different instance of what we want to look at in a data frame. So like I said, kind of similar to a spreadsheet or a table, as you've all seen in high school. To create a data frame, we have a couple different options. We can essentially pass in a dictionary. So given this dictionary, we'll be left with a data frame that looks like this. Essentially, each dictionary represents a different row in the data set. So for example, 0, we have 1, 2, 3, 4. For example, 1, we have 100, 200, 300, 400, and so on. To select columns in our data frames, we use square bracket notation. It's simple. It's similar to how you'd access a dictionary value. So in this case, if we want to check what values are in the A column, we use bracket notation. And we are given the A column as something called a Pandas series. This is essentially a one-dimensional array with labels. We can also kind of extract multiple columns using commas in our bracket notation. So if we want to get A and B, we'll be given this data frame. To select based on indices, you use iloc, and again, this will be a series. Similar to how we did slicing in NumPy arrays, we can use slicing in the iloc function to get multiple rows. And another common way to create data frames is importing it from an existing CSV. We'll use a function called pandas read CSV, and that'll load a comma-separated value file into a data frame. So in this case, we're going to be using an SAT versus GPA CSV, and we're going to load it into df2. So as you can see, we now have a full data frame of each different example with its SAT score and GPA. And note, this is, I think, on the old scale. Yeah, it's definitely on the old scale GPA or old scale SAT. So it goes up to 2,400. Don't worry, they're not giving people 1,700s on the SAT anymore. Really quickly, one of the things that Pandas is often used for is data manipulation and data pre-processing. So in the case that we have null values, we can check with the data frame.isNA value, isNA function. In this case, it just gives you a data frame full of Boolean values. The way that we can check if a single column has any value that is going to be NA or missing, we use the .any method. And this will just tell us, okay, we don't have anything that is missing in this data frame. That's pretty lucky for us. Typically, you won't have that. So let's look really quickly in the case that we do have some null values in this data frame. So we have a couple of NaN values. We can simply fill those by using fill NA and specifying a value to fill. So in our case, we're just going to fill it with 0. I'll do this one or you're good. Okay. Finally, last but not least, we're going to cover matplotlib. Matplotlib is used in data visualization. It's really useful, like just full stop. You're going to use this a lot, especially when you're starting out to look at the data, look at different distributions, and kind of see what you are dealing with and how you can handle it. So we're going to import its pyplot module as plot. And then we're going to generate a graph of the sine function. So essentially, the way that matplotlib works is you're going to specify different attributes that you want the graph to have. So in this case, we're specifying an X label, a Y label, and a title, as well as telling it that we'd like to see the grid lines of this function. And then finally, you run plot dot plot of your X and your Y values. And typically you will have to do plot dot show, depending on your environment, but in Colab, we don't have to do that. We can also do some scatter plots. So just a couple of random data points. We can also specify colors. We can specify the markers, so on and so forth. And we can also just do bar charts. Yeah, there is a ton of different plotting functions, a ton of different graph types that you can run in Matplotlib. The documentation is included in this notebook. I highly recommend, if you're interested, taking a quick look at that. Other than that, I think that is our full workshop. Thank you so much for coming. We will see you. We have one next week, right? Next week.
Thank you all so much for coming.